All right, we're going to go ahead and get started here. Hello, everyone, and welcome. Thank you for choosing to spend your valuable time with us. Today's webinar will cover the new and updated Getting Started with wolfMQTT, presented by wolfSSL Senior Software Engineer Eric Blankenhorn. My name is Emma, and I will be moderating the webinar. All attendees will be in listen-only mode. If you have questions, please use the Q&A box. After the presentation, Eric will answer your questions. As always, our webinars are recorded and made available on our YouTube channel. If you'd like to stay updated with all the latest from wolfSSL, follow us on Twitter, connect with us on LinkedIn, and subscribe to our YouTube channel. Feel free to contact us via email at facts@wolfssl.com if you have any further questions. Before we dive into the technical presentation, I'd like to provide a brief overview of wolfSSL. Today, wolfSSL secures over 2.5 billion connections. We have more than 2,500 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, primarily engineers. This progress is, of course, supported by a strong partner network that we are very proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, a FIPS 140-3 certification, and a FIPS-ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfboot, Java wrappers and JSSC support, and commercial support for curl, and our newest product offering, wolfHSM. These offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. Now I would like to turn it over to Eric to discuss new and updated Getting Started with wolfMQTT.
Excellent. Thank you, Emma. Hello, everyone. Thanks for attending our webinar. I'm Eric Blankenhorn, an engineer here at wolfSSL. I'll be discussing the basics of the MQTT protocol and how the wolfMQTT client library can help secure your IoT network. We'll start with a discussion about the specific needs of the Internet of Things, which will lead us to an overview of the MQTT protocol itself. Next, we'll review the different specifications that are supported by the wolfMQTT library. Then we'll take a look at the architecture of the library, integration with wolfSSL, and a quick look at the configuration options and the build process. That leads us to talk about the many rich client examples available alongside the core library. Next, we can look at last year's releases and some of the ideas we have for the roadmap of wolfMQTT. And lastly, we'll answer any questions that you might have about the protocol or wolfMQTT specifically. The primary concern of many IoT projects is one of resource constraints. These devices may have tight power budgets or small memory availability, or they might be operating on networks that are either unreliable or expensive, each of which requires minimizing the amount of data transferred. The MQTT specification is free to use, which has greatly enhanced its popularity among developers of devices that number in the tens of billions. Since the protocol is easily scalable, industries across the spectrum have found it to be suitable to their application. Also key for developers is how friendly the API is. There are really only 8 primary functions in the wolfMQTT library that needed to have a fully functioning client. So MQTT, it stands for Message Queuing Telemetry Transport, or MQ Telemetry Transport, depending on who you ask. It was designed specially for lightweight embedded type systems, but it's scalable to allow for efficient large networks also. Individual MQTT packets are very small, and publishing a short message, including the overhead, is in the tens of bytes. The publish and subscribe methodology allows publishers to send lots of small bits of data that are related to a topic. Then that data will be sent to the subscribers of that same topic. This allows a loosely coupled system in which devices do not need to have state knowledge of their peers to communicate with them. Through the use of gateways and bridge devices, the peers don't even need to exist on the same network topology. Even more important to the devices that may be powered off or to conserve resources, messages can be stored and resent until the transmission is successful. So brokers are the central point of contact for all of the MQTT clients. Brokers act as the directory of all the connected clients, the index of all the topics, and the distributor of all the messages. So choose your broker wisely. The protocol specifically recommends using TLS to secure MQTT traffic. Devices that need to go offline to conserve power can use session resumption to quickly reestablish the connection. This level of protection adds overhead, but luckily we have the world's best TLS library available, wolfSSL. So quality of service, it's useful for defining a message's integrity. Things like network capability, tolerance for missing data, tolerance for duplicate data are all considerations when choosing the quality of service level. When a client subscribes to a topic, a QoS level is specified. Likewise, when a client publishes to a topic, a QoS level is also specified. The highest QoS level is determined by the party with the lowest QoS. In other words, client A can publish at QoS 1, but if the subscriber client B used QoS 0, then the client B will only be sent a QoS 0 version of the message from the broker. With QoS 0, the broker does not acknowledge the receipt of the message, and the message is not stored or retransmitted by the sender. QoS 0 is best suited for a stable network or non-critical data. Imagine something like a rain gauge sensor that reports data every minute. So a couple of minutes of readings lost here and there is probably okay. With quality of service 1, the sender stores the message until it gets a PUBAC acknowledgement packet from the receiver. In this case, a message could be sent or delivered multiple times. This is suitable when data is critical. In other words, it must be delivered, but it's okay if duplicate data is received. Furthermore, network restrictions like bandwidth or cost might not allow for the full QoS 2 handshake, which we'll talk about in a second. Example here, you can imagine like a blood pressure monitoring application that sent reports from the sensor containing a timestamp and the BP reading of an astronaut. The application can ignore readings with the same timestamp, but all the readings have to be recorded. That would be a good candidate for QoS 1. And QoS 2 is the most thorough, but it's also the most costly. It takes 4 full transactions for each published message to complete a delivery. QoS 2 should be used when the application cannot handle multiple messages and repeated data. For example, a firmware delivery that would waste precious network bandwidth receiving a duplicate message, or perhaps require all of the device's storage capacity to even receive the payload. Speaking of payloads, the MQTT specification allows up to 256 megabytes of payload per message. However, the actual payload maximum is often limited by the broker. For example, the limit for AWS is 128 kilobytes, last I checked, while Azure limits to the client to broker transfers to 256 kilobytes, and broker to client messages are limited to only 64 kilobytes. So again, choose your broker wisely. The last will and testament that allows other clients to be informed when devices have lost their connection to the broker. During a normal session, a client would disconnect cleanly, indicating an intentional, orderly shutdown. But if a broker loses the connection ungracefully, then the disconnected client can inform its peers using the last will and testament message that's stored on the broker. Also, as you can see, there are only 14 packet types for the VU 3.11 protocol. So packet sniffers like Wireshark, they're aware of MQTT traffic by the packet header. And it can be very useful for a client application to send a single subscribe packet or on initialization and be notified of messages from multiple topics. The term publish here, it really refers only to the message type. A message that is published by a client will be sent to the broker. The broker will then publish that message to all the clients who are subscribed to the message's topic. Messages can also be marked for retention to be stored on the broker. If the message is retained by the broker, then new clients will be sent that message when they first subscribe. This can be useful for conveying information like system state. So version 3.1.1 is the successor to version 3.0, and it's the only version of the protocol currently supported by AWS and Azure. Actually, that's changed now. I think AWS does support version 5.0. Most implementations of MQTT are using the de facto 3.11 version of that protocol. Version 5 was completed in March of 2019. It had support for properties to be sent along with the command packets. Properties are a simple way to add custom metadata to uh, the to the packets in the form of key value pairs. These can be used, for instance, to describe the format of the payload data. Recovery from command line failures can be complex, and new error messages from the broker can be used to help the client know what went wrong during a failed subscribe or publish. And then topic aliasing. This allows integer representations of complex topic names. This can significantly reduce the bandwidth required for messages. Here's a little bit of trivia for you. So what happened to the version 4.0 of the MQTT protocol? Well, the connect packet defines the 8-bit unsigned protocol level field. So a value of 0 by 3 corresponds to version 3.1, and 0 by 4 came to mean 3.1.1. And so logically, 0 by 5, hex 5, became version 5.0. The sensor network protocol, it was developed around 2009 to enable battery powered devices on low bandwidth wireless networks to benefit from MQTT. The SN protocol allows a gateway to device to communicate the full MQTT messages to a broker over a normal TCP capable network. Message packets from an MQTT SN client are even smaller than MQTT through the use of topic IDs or a 2-byte value that's used to represent the topic name. So let's talk a little about wolfMQTT specifically. Excuse me. The MQTT wolfMQTT library is organized into 3 distinct components: the client, the packet, and the socket. The client contains the actual API functions listed here. Just connect, disconnect, publish, subscribe, unsubscribe, ping, and wait message. The packet component is where you can find all the internal functions for building and parsing the packet structures. And lastly, the socket component is the interface for the lower level networking layer. This could be straight through to TCP, or it can be enabled to use TLS courtesy of wolfSSL. You can even pipe the IO through some other peripheral, such as a serial port. So here, I'd like to cover how wolfMQTT interfaces with wolfSSL to connect using TLS. The NetConnect API establishes the socket connection before any actual MQTT packets are transmitted. There are 2 parameters related to TLS here, the flag to use TLS and the optional MQTT TLS callback function pointer. A call into the socket component initializes wolfSSL and calls the passed in TLS callback if it was provided. Else, the default TLS settings are used. Then the socket receive and send functions are registered with wolfSSL. At this point, all MQTT library IO will be piped through wolfSSL using a secure connection. A bit more about the MQTT TLS callback. It's used to set up application-specific certificates or settings for the TLS connection. Here you can set up things like OCSP, mutual authentication. You can specify cryptographic algorithms and ciphers, or any of the fine-tuning enabled with wolfSSL. You can also set up a verify callback, which can be used to override client-side failures during the TLS connection. Or you could also use the callback to do additional verification of the server certificate during the handshake. The verify callback also takes a user customizable context field. In the examples, we pass the MQTT client structure, but it could be any data relevant to your application. So as you can see, it's easy to configure the library for the various protocols and features that are supported. If you disable TLS support, then the wolfMQTT library can actually be compiled and run completely independent of wolfSSL. But many commercial brokers require TLS to be used for authentication and encryption. Debug messages, they're crucial for figuring out why your application is not quite working right. The last one there, multi-thread, that allows independent tasks to use the library without any internal conflicts. This adds some overhead, so we made it configurable so as not to bloat the library for size-conscious applications that are single-threaded. Building the library, it's very straightforward. As I mentioned before, if you want to use TLS, then wolfSSL must be installed first. After cloning from GitHub, you simply autogen, configure, make, and that's it. So it's about 16 kilobytes for the full library. But of course, you can pare that down if you're only using, a couple of the API. So now let's talk about those examples I talked about earlier. So examples, they're crucial, but often an overlooked part of any successful library. We've taken the time to share as much as possible. The standard MQTT client example is quite powerful. You can specify a host, port, QoS, topic name, etc. Pretty much everything you need to test a broker connection. It's also where the MQTT v5 specific samples live. The non-blocking client, it's of course very popular with the microcontroller crowd. The multi-thread example uses a publish task, a subscribe task, and a message wait task, and a ping task to demonstrate that feature of the library. The firmware example is pretty nifty. It has two parts. The first, the FW push, uses wolfSSL to build a hashed and signed firmware image and publish it to the broker. The second part, the FW client, is subscribed to the topic and waiting for the firmware to be published. When it receives the message, the firmware image is unpacked and verified. Whereas the other examples use a couple of shared utility files, the MQTT simple demo is completely self-contained, and it's very straightforward. The sensor network client requires another component besides the broker we talked about earlier, the gateway. The gateway handles communication over UDP on the sensor network side and retransmits messages to and from a broker on the TCP side. And then we also created some new atomic publish and subscribe examples, and these are going to be just basically on the command line, you just specify the broker and the topic and then a message and it'll publish it, or you can just specify the broker and a topic and it'll subscribe to it. So based on support questions and interactions we've had, these brokers probably account for 80% of the wolfMQTT client library usage. The commercial IoT industry, cloud industry has been consolidating over the past few years. There was IBM's Watson IoT that shut down in December 2023, and then Google Cloud IoT Core was actually shut down in August of 23. So again, choose your broker wisely. So those are examples. They're all neatly contained in the examples folder. There you can also find a couple of utility files that contain code that is used by the examples, but not necessarily needed in the wolfMQTT library proper. The simple client executable is about 9K fully built. You can see in the output that the client is connecting to the test.mosquito.org public broker on port 8883 using TLS. You'll also notice that there's an error. That was because we did not load the CA certificate intentionally, just to exercise the callback. You can see that the callback overrides the error and allows it anyway, and then it connects, subscribes to a topic, publishes to that topic, and receives the message on the subscribe side, and then publishes another one, and we can confirm that yes, this webinar is awesome. Um, then to end this client's example, you just use Control C, and the example will unsubscribe from the topic and disconnect from the broker. So let's talk a little bit about what we did last year. As you can see, we've been pretty busy adding features and improving the library. We aim for quarterly releases, though we make some exceptions for critical issues that might get reported. As wolfMQTT matures, we'd expect the development to taper off, and this was a little evident last year with only 2 releases. We improved the multi-thread functionality and added more testing to catch issues in the future. We also added an integration with curl. It's kind of a unique use case in which curl acts as the transport layer. We also added an Expressif module for all you ESP32 developers out there. And while not directly related to changes in the wolfMQTT project, we did add an open source port for the Mosquito MQTT broker project, in which the default OpenSSL TLS backend is swapped for wolfSSL. This gives users of Mosquito all the benefits of wolfSSL, including smaller build, greater performance, and FIPS 140-3 certification. And then this is where we are going. This list consists of things that some folks have asked if we have, and some things that we just think would be neat to have. We've had some inquiries about developing a wolfMQTT based broker. This would be intended to run an embedded microcontroller, maybe. It would have limited or configurable capabilities to start with. We already added support in the MQTT SN library to secure communications using DTLS 1.2. As a next step, we will also like to develop a gateway solution to take advantage of wolfSSL's recent DTLS 1.3 implementation. More testing, it's always welcome, and we are investigating existing solutions for protocol compliance testing. We've had a couple of users interested in wolfMQTT supporting WebSockets natively. We would likely utilize the libWebSockets library that already supports using wolfSSL for TLS. And we're always interested to hear what else we should support and other ideas you have. So please keep those suggestions coming. And that brings us to the end of the slides. So now I'd like to open the floor to questions.
Amazing. Thank you so much, Eric. Okay, to start off the questions, is wolfMQTT FIPS certified?
Okay, yeah, so the wolfMQTT library itself is not FIPS certified, but that's because the FIPS certification really only covers the cryptography that's being used. So even though wolfMQTT is not, wolfSSL is or can be FIPS certified. We have a FIPS certified solution all the way up to version 140-3 of that certification. Our certificate was released last year and approved, and you can actually go on the NIST website and look us up on there. And so you can actually run a FIPS certified wolfMQTT client by using wolfMQTT with the wolfSSL wolfcrypt FIPS approved library.
Wonderful. Moving right along, can wolfMQTT use a non-socket-based interface?
Yeah, so it's actually quite flexible. From the design of wolfMQTT, we basically designed it such that you can use callbacks to interface to set up the IO interface. Um, So in doing that, you can actually plug in everything from like I think we talked about a serial example where you're basically doing MQTT over a serial port. We also did the curl integration I talked about earlier. So that was pretty neat where we actually MQTT works using curl as the underlying transport layer. So you basically set up a connection using curl, and then wolfMQTT uses the curl easy IO API to do the actual transmission. And so then you can have curl built with wolfSSL and set up a TLS connection, and then you can actually do MQTT on top of that and never have to do a TCP socket interface.
Awesome. Can I build Wolf MQTT in Windows?
Oh yeah, of course. So we actually have a Visual Studio project um, in the root of the library that you can build for Visual Studio. We also have a VC package if that's the build system that you're more familiar with. We also have support CMake. So if you're using VS Code and you like CMake, then you can use that method for building. Pretty much you name it, we've touched it before, and we're happy to point you to other examples that we might have for other IDEs.
Amazing. Well, thank you so much, Eric, for hosting an informative webinar. Thank you to everyone for joining. I will email a copy of the webinar recording and PDF slides. You can keep up with our upcoming events, meet our team in person, read our blog posts, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any questions, please reach out to us at facts@wolfssl.com. Thank you again, and we look forward to seeing you tomorrow for the new and updated Getting Started with curl. Thank you all.